Hi. In this video, we are going to learn about Markov chains, which are special cases of stochastic processes. What is a stochastic process? Think about a system and a characteristic of that system. We'll see some examples. And let's say you don't know how that system works. That characteristic changes over time. So to you, that characteristic is totally normal. I mean, random, sorry. Um, so, and you're studying the behavior of that system based on that characteristic over time. Now, if the time is continuous, it's a continuous time, a stochastic process. And if time is discrete, for example, you're checking the status of the system with respect to that characteristic every minute, every hour, every day, every week, every year, depending on how you define your time units. If the time is discrete, you call it a discrete time, a stochastic process. Markov chains are special cases of a stochastic processes where past history of past history of the system with respect to that characteristic has no impact on what is going to be the next state. We will see some examples of those. Okay, but the key is this: that characteristic that you're monitoring and can assume different values. Those values are called the states of the system, and those states to you, because you don't know what's going on inside the system, randomly change. All right, let's look at one example. So let's say the system is human being, someone, an individual. Let's say a new employee that has been hired in your company, and you don't know anything about them. You don't know anything about their personal life. So let's say one characteristic of that person is their emotion. So what states can that emotion have? Happy, sad, indifferent, angry, and probably many others, depending on the individual. Okay, so here on the x-axis, I'm looking at time, and let's say every day you see that person. The first day you see them, they're pretty happy. You don't know why, you don't know them. The next day, they're very excited. They're talkative and chatty, very excited, high energy. Next day, they seem pretty sad. You don't know anything about them. Let's say you're not talking to them, okay? To learn what's happening. The next day, they're very angry. So the state of the person's characteristic, which is their emotion, keeps changing to you, and you don't know why. So it's totally random to you. Next day, they're happy. The following days, again happy, and then excited again, then happy for a while. So it means that I'm not going to talk about the steadiest states yet, but it seems like they're settling down on that mood of happy. Maybe the first days in the company, they were not very stable, right? In terms of knowing their job, knowing the people they're going to work with, and all of that. Okay, so the key point here is that the other state is randomly changing. Our goal here is to create a transition probability matrix for any given stochastic process, where we can see the probability of going from one state to another. All right. So this is one example. What really happened probably is the first day they were happy that they finally got a job, and then next day they probably were going to an exciting party, and that's why they were excited all day. But something happened during that party. We don't know what happened. We can guess. Next day they were very sad because of what they saw, and then the following day they probably talked to some friends and figured that why that thing they saw at the party happened, and then now they're angry, and then they're sad again, and then they talk to more friends, and now they're happy. All right, now they're excited about their work and so forth, but we don't care about this. A lot of systems, we don't know what's going on inside them. That's why we're studying them as stochastic processes. A lot of equipment, we don't want to get into the failure mechanism. A lot of studies on the society, we can't really see the mechanism, the very complex mechanism of a society. So we look at different characteristics over time and we see how they randomly change, and we use that to basically predict the steady state or how the system is going to settle down in the future. All right, let's look at another example. Another example is the weather. The system is environment, characteristic is weather. The states could be rainy, sunny, cloudy, snowing, right? And let's say you don't know anything about weather prediction or anything about physics, basically. Then what's happening to you is totally random. Today is sunny, next day is rainy, so you can't really have any predictions. It seems to you very random. That's another stochastic process. And note that we cannot have here, we cannot have two states at a given time. All right. So let's make it a little more formal. Let's define x sub t as a random variable that shows the state of the system at time t. Okay. A discrete time a stochastic process is basically a collection of these random variables. So x sub 1 is what's the emotion of your colleague on the first day, on the second day, basically. X sub 0 is the first day you meet them. And it's totally random to you. It could be anything, right? X sub 2 and so forth. Or for the weather, it's what kind of weather you're gonna have on that day. So here, for example, x sub 4 means on day 4 or day 5, the weather is in a state 1, and a state 1 is defined as sunny. I think you got that. So let's look at an example. Let's say we have someone, a gambler, who has $2. So x, and the state of the system is the characteristic of the system is the amount of money that individual has, and the states could be the dollar value, right? So it starts with $2, and the game has some rules. For example, if you win, you will gain $1. If you lose, you will lose $1. Every time you're betting on $1, basically. And the probability of winning in every round of the game is P. Probability of losing obviously is 1 minus P. So the goal is to increase your money to $4. Means that the game ends once you have $4. Also, the game ends when you have $0 because you don't have anything to play with, any money to bet on. Okay, so x sub 0 is how much money you started with, which is $2 here. X sub 1, what can it be? You either win or you lose. If you win, you're gonna have $3. If you lose, you will have basically $1. So it could be 3 with probability of P winning, or 1 with probability of 1 minus P. And then x sub t, if at some point in time in the future you have $4, after that, because you're not playing, x sub t plus 1, for example, and note, t here, time here, is not really time, it's rounds of the game. That's why a discrete time stochastic process describes this very well. So x sub t is $4, so after that, all of them are going to be $4 because you're not going to play. And they don't really mean anything because you're not going to have any time after that. You're not actually playing. There are not going to be any more rounds. Same thing with x sub t. At some point you lose all of your money. If at some point you have $0, after that your state is just going to be $0. All right.